All right, thank you all for coming to Functional Programming in Java. I'm Martin Snyder. I'm the VP of Engineering at Pinnacle 21. I'd like to thank not just the attendees, but the JUG organizers for inviting me. I'd like to thank Cerner for hosting us, Pinnacle 21 for providing the food. Pinnacle enables life sciences companies to measure and improve the quality of their submission data. We're going to be talking about functional programming as a kind of a survey lecture of covering all of the basics for people. This is designed for people that are new or unfamiliar with functional programming, but are strong with Java and have been programming in Java for a while. So we're going to, at every opportunity, talk about functional programming influences or opportunities in the Java language. And the goal of all of this is to inspire further learning for those of you in the audience or watching the video. And functional programs, it's all inspired fundamentally by mathematical functions. And I have some examples here. You know, y equals f of x is an easy one, z equals g of y. It doesn't have to mean anything. People know generally what the properties of these things are. And then we can see that z, which was g of y, could also be expressed as g of f of x. And we know intrinsically as people that completed high school mathematics that those two things are equivalent. And we also, like to show off the slideware here. So we have omega equals sine of theta. That's a pain to do, but it was part of the example, so I stole it. And when we get to functional programming, we're going to see functions that look more like that last one. So some new generation of the state equals a function that applies some impulse to an existing state. And that's where we're headed in terms of mindset. This is important because we don't care about mathematical functions by themselves. We care about the properties of mathematical functions. And fundamentally, the most important part is that mathematical functions will never hurt you. They won't behave differently one day than the other. They won't do unpredictable things. They won't stop working when you upgrade a dependency. So there's a lot of things that as programmers, we wish our programs behaved in these ways. And we saw from some of those examples before that the dependencies are always explicit. We know when we say y equals f of x, that y depends on x. We know that, and it depends on nothing else. There's no hidden magic. There's nothing going on behind the scenes when we have mathematical functions. So everything that we're going to end up talking about comes from that. And there's a series of logical implications that is produced from this. So functions themselves, they imply immutability. They imply a world where things do not change unexpectedly. If I compute the value of f of 3, it will always resolve to the same thing. There's no circumstance where it will suddenly start producing a different value. And likewise, that input that I put in, that 3 that I give to f, always means the same thing. It's never going to change unexpectedly. So f can evaluate consistently without consideration for some odd influence coming on. And that immutability, that notion of immutability, has a series of other implications. And we're going to go through all of these terms, and we're going to see examples of how all of this works within functional programming concepts in general, but specifically in Java. So immutability implies these things called persistent data structures, which are immutable by nature. And persistent data structures by themselves force you to develop techniques of recursion. And recursion by itself forces you to have higher order functions. These are primitive concepts in functional programming, which are the building blocks. And then separate from that, immutability is going to imply expressions, and expressions imply this mathematical concept of referential transparency, and that leads to lazy evaluation. Lazy evaluation ends up being hugely important if you want a compiler for a programming language to make optimizations on behalf of the programmer, especially ones they didn't anticipate. So when you talk about like computer science and the fundamentals that launched the modern computing era, this is where a lot of these things start. And you don't have to know this stuff to be effective in the industry. And you don't actually have to know all this stuff to be effective, especially getting started with functional programming. But I think it is interesting to see how these different concepts build on one another. So immutable is the first concept. We pull the definition from the dictionary. And the important notion here, it isn't that something immutable doesn't change. It's that it can't change. And that's a distinction that's important in Java, because a lot of, when we get to the immutable examples in Java, it's things that they look like they might be able to change, but they don't actually change, and you can take advantage of that. it's more valuable to have something that by its very nature is locked in and can never change. So that's something that we would strive for in developing functional programs. There's a lot of benefits of this. I mean, I talked a little bit about how you're defending against the unexpected. A nice thing about an immutable object is you never need to copy it. You can share as many references to that object as you like, and everyone can do anything they want with that. And you don't really there's nothing to think. There's no cognitive load. There's no cost as a conceptual cost as a programmer in doing that. You can cache an immutable value for as long as you want. It's never going to change. You don't have to recompute it. There's a technique called memoization, which is exactly that, of taking the result of a function, an expensive computation, and remembering what that is for the next time. You never have to synchronize. I mean, synchronization, talking about like mutexes and locking and semaphores and all these things, it's a challenging part of computing, and you only have to do that for things that might change. If it would never change, you only have read access, and read access can be concurrent at no cost. And then also copies are interchangeable. Like I can do an optimization in a functional program. If I have 18 objects which are all the same, say, XML structure, I can sweep out 17 of them and make them all point to the same copy. That's a safe operation because knowing they're equal at a single moment in time implies that they will be equal forever. And that's not the case, of course, if you don't have immutability. And you'll see a couple of these things, I was talking about changing things while they're in memory, they imply some sort of garbage collection. And so you'll see that almost every functional language is a garbage collection language, and that's part of why, is that you don't want people to have to do a lot of these things in their own minds, or you don't want them to have to do it in the programming language, so it's easier to do that. And then there's ways you can achieve the same thing without garbage collection. They were popular in the 80s. I don't think anyone does them anymore. So let's talk about Java for a second. The final keyword is your primary tool if you're trying to make things immutable on your own. At first glance, it looks like this was modeled on the const keyword from C++, and a lot of concepts in Java came from C++. Final is much less powerful than const for people that were fans of that. So final just is, in a very limited sense, this one value can't change. But if I have an object that's final, my reference to that object won't change. But if it's a mutable object, then I'm in trouble. So to use final in Java, we have to use it everywhere. If I had an object itself where every field was final and a final reference to it, then I'm starting to be in the immutable world. And when you talk about things like getters and setters, of course I wouldn't have any setters. And then whether or not you have getters on a final property is really up to you, because that's just a question of how you design your API. Given that it's never going to change, it doesn't really matter how you're going to control access to it. Strings, of course, are immutable in Java from the very first version. And I don't know how many people in the audience worked with that first version of Java, but for me as a programmer, when I was doing that, it was uncomfortable at first. Like, the first thing you would do in a C++ project was you would write a string class. That was basically the 90s. And so you get to Java, and you're used to writing these really sophisticated string classes, and now you get one for free, but it's immutable, and at first that's frustrating. You're expecting something else. And I think in today's world, that doesn't bother a single person. People just are, and it's a good testimonial to the fact that immutability is at first uncomfortable, but really has a positive impact, and is not the kind of thing that gets in people's ways. All the numeric objects in Java are immutable. This is not an interesting topic for a lot of people, including me, so we're just going to move on. There was an era where Guava collections were popular, and they were pushing a lot of functional programming principles, including immutability. This has fallen out of favor just as Java as a language has kind of caught up in those areas. So, but it's an important part of the Java history, I think, to mention, even though it wasn't part of the actual language specification. And then when we get to Java 8, that's when from a design standpoint, the functional concepts and immutability in particular starts to come into the language more. And so in Java 8, we had a streams API, which you can use in a lot of different forms, but the primary way to use it at that version at that point in time was to get an immutable interface to one of the collection classes, so that you could then perform a series of operations. And it turns out that Java 8 streams are going to encompass a lot of the concepts that we're talking about today. And so that's something that's really important to keep coming back to. And then in Java 9, they implemented actual singleton, or not just singleton, but other factory methods on the collection classes to build immutable objects conveniently in the Java language. And this is an important concept also, because I think one of the reasons that Guava did not take off more is that it suffered from extreme cases of syntactic inconvenience. It was very painful to do what you wanted to do. It was a verbose syntax. You had to really type a lot of code to do some things that were relatively simple. And then later on in Java's evolution, as they started to address some of those concerns with things like lambdas in particular, not only did they made it so that Guava would have been more successful, but also that it was less necessary. So we're going to take a look at an interesting case. I mentioned how you could find common objects in memory, and you could sweep them and push them into one object. And Java actually has that capability, and it had it from the very beginning. So it's kind of interesting. People don't think of Java as a functional programming language, but it has one of the more esoteric use cases of functional programming languages built in from the first version. And I can see that here, where I have a couple strings, lines 1, 2, and 3. I've made 3 strings, the third of which happens to be a concatenation of the first 2. And then in line 4, I'm going to concatenate the first 2 at runtime instead of compile time. And then I can use this intern method to see what it does. And then we see in the output of this program. And this code and all the code that I'm going to share here tonight is available in a GitHub repository. I have the link at the end. And it's important, I think, for people that are interested in this to just step through the examples. They're all very compact, but seeing this stuff in action is really illustrative. And what we see when we run this is that the compile string and the runtime string are not equal in terms of reference equality, but when I compare that optimized string to the compile string, they are exactly the same object in Java. And it's easy to see, I think, in the context of this discussion, why that works and why that is something you might want to do. Not for a string that's 6 characters long, but exactly in a circumstance where you're loading something like a large document into memory. And you might have concurrent access to such a thing, and having 3 users load the same document would be very inefficient versus being able to share that object in a light cache. And then we talked about how the stream interface provides immutable transformations, and we have a kind of a contrived example here to look at that. And the most important thing in the whole example is that this underlying array never changes. So I take an array of the first 5 positive integers, and I convert that to a stream in line 3, and then I can do a map, and a map is a transformation operation. So we're going to keep the array length the same, but we're going to apply this function to multiply an element by 2 to each element. So then we're going to get the even integers 2 through 10. And then filter is not going to change any of the individual elements, but is going to change the array itself in a reductive manner only. So we're going to end up with the positive integers 2 through 10 that are greater than 5. Flat map can change the nature of a single element in either direction. So it could eliminate an element reductively, or it could expand an element into multiple entries. And that's what we do here. We take every element there, so now we should have 6, 8, and 10, and we're going to add each one twice. So we'll get 2 6s, 2 8s, and 2 10s. And then reduce is going to kind of scan through the entire stream at that point, and it's going to compile it into a single value. And in this case, it's going to be a single integer, and we're just going to add everything together. So 2 6s, 2 8s, and 2 10s. We add all that together, and hopefully we get 48. I'm pretty sure that's the case. It was when I ran it. And in doing all of that, we never changed the original array, and we never specified at any point how we're going to do immediate storage or when these operations are going to happen. So we're skipping ahead a little bit, but there's a lot of optimization, room for optimization in terms of language, in terms of the JVM, in terms of library design, because we specify so little here. And you can imagine if you were doing all this work by hand, you would get wildly different properties if 10 different engineers solved this problem, 10 different ways in terms of memory consumption and runtime stuff. And so this puts you in a better position where you're specifying the sequence of events and you're less involved in the individual details. And then this slide we're going to skip past, but this is just a text expression of what I just said for people that are following along in the video. If you just want to see a little more, because these are really common operations in functional programming. You'll see these terms a lot, especially like map and flat map. Anytime you see those 2 methods on an object, if you're trying to learn about functional programming, just call them and don't call anything else, and you're headed in the right direction. And then reduce is really popular in terms of data analytics, and I'm sure people are most familiar at this point with map reduce. It's like it was named based on these things, and it did exactly map followed by reduce. And then the Java immutable collections, like I said, they're not what I would, and I think a lot of functional programmers would like to see in terms of immutable collections, but they are at least immutable. When you create them, you can trust that they will never change. But they implement the standard collections API. So in the example I have up here, we generate an immutable collection, and then we try to add something and we'll get an exception. So it's not ideal. You can trust them, but as a programmer, like you don't have that impression when you're past one of these things. You don't know for sure that it's immutable. So it's a step in the right direction, and it's just, I think it's reflective of the fact that Java is moving in this direction versus when it started in this collection. Almost every single functional programming language starts with immutable collections API. I want to talk a little bit about what happens if you take away immutability, because everything that I'm talking about starts with this base assumption that immutability is so important that it implies all of these other things. And if you can attack immutability and say, well, that's actually not that important, well, then maybe everything else isn't important either. And so I think it's really important, given that that's the nexus of everything I'm discussing, that we talk just a little bit about what happens if you don't have it. And so this is a nice quote from Stu Holloway. He's the founder of Cognitech, which they do Clojure, basically. They own the Clojure programming language and have the language inventor on staff there and everything. It makes a good point that managing state is the major issue with programmers in general. And if you're not sure, just remember that if almost any electronic device, if it's not working correctly, you turn it off, turn it back on. And all you're doing is resetting the state and getting back to a known state and moving forward. And immutability is always about maintaining a known state and never having an impossible state or deviating from something that's expected and stuff. So the fact that this statement is true and trusted by everyone indicates the counterexample just a little bit. I can do better than this, though. Imagine a person object. People have written a lot of the easy example people can conceptualize. We have a first name and a last name. And when we're going to two-string it, we're just going to concatenate the two with a space. Equals hash code. We know how to implement them, but we usually don't. We let the software implement it for us. And if you look at the code example I had, IDEA just generate these things. And so I've intentionally made this mutable. I've just made the two members public. I could have added getters and setters. I'm just trying to keep it compact to fit on the slide. So we have an object for Martin. I'm keeping it as S, so in the output we fit without having to scroll. I run into that problem later on. So I make an object, I add it to a set of people. I add myself on line 4. In line 5, I give myself a nickname Marty, and then I add myself again. And who here knows for sure what's going to happen there? How many objects are going to be in the set of people? Right? Because I've added the same object twice, but at the time I added it, it actually had different attributes. And some people might know, some might not. It doesn't really matter. The point that it's even ambiguous and worthy of discussion already indicates that we have a problem. And then what I'm going to do to really illustrate this is I'm going to copy the set. And most people, I think, would fairly expect that when I copy a set, the new set is the same as the old set. That's a fair expectation of copy. And when we look at the output, we'll see that that's not what happens at all. When I look at the contents of people, it has 2 copies of Marty S. Right? So the original Martin that was added doesn't exist. And I ask if it contains Martin, that's false. But that was the first thing I did, was add Martin. Right? And I can explain this away, but I'm not happy. Right? The size of people is 2 to answer that question. So I added the same object twice with different values, and I got 2. And I can explain why that is. It's not important. But when I copy it, I correctly get 1 value. Right? It's easy to see why copy reduces to 1. It doesn't matter who's at fault here. This is a nightmare. This is why I talk about the perils of mutability. And you can say, oh, well, look, just don't do what you did there. But the problem is that line 4, that might be like the nexus of a processing narrative, taking an object off a connection and putting it into a set or a map or something like that. And this line 5, where we modify it, that could be deep in my programming logic. And if that's the case, debugging this is really, really hard. I mean, you may never debug that because you may not be able to come up with a valid reproduction scenario. Now, maybe after seeing this presentation you will, and you know to look for this stuff. But it's better to not even be thinking about this in the first place. And so this, I think, is really illustrative. Compact example, but you can create nightmares for people, intentionally or unintentionally, just by allowing mutability in the first place. So we're going to keep rolling. We have a lot of material to cover. Persistent data structures, we're going to skip the actual definition there. It's a structure that every time you change it, it keeps a copy of its previous version. And that's really helpful. So if I had a reference to a set and someone adds it to the set, my reference is unchanged. I still have that old version. They've generationally created a whole new copy. Every time you change a persistent data structure, the original is still available somewhere if anyone cares. If it's not, it would get garbage collected. And what you have is a whole new object, which in most every case, would reference that previous generation. And we can see this really easily with a list. So I mean, when you go to like, first day of your first computer science class that involves functional programming, you're talking about lists typically, in no matter what language. And a list is defined to have a single element at the head of the list and then a tail, which is another list. And so it's easy to see how if I were to add something, I wouldn't change this. I would just take a whole new element at the head and point to this existing list. And that's exactly what people do. And I wouldn't worry too much about the exact structure of this, just knowing that it's a single element and the tail is a whole element. And then we have to worry about this problem of, well, what if I have an empty list? And so we'll just define that to be its own special thing. And so a one element list would have a single head pointing to the empty list. And we can define that. And we're not trying to create an API that other people are going to use. So I'm just throwing exceptions. If you try to operate on an empty list, that's your fault. You should have called it as empty. And then we can see how the implementation of node and empty are both pretty straightforward. Okay. So we're not going to dwell on this too much, but it is useful context to talk about recursion. So recursion is when something kind of feeds back on itself. And we know for certain that we need this because list itself was just recursively defined, right? A list doesn't exist without the notion of its tail, which is also a list. And anytime you see that, like if, for instance, you were in an interview scenario and someone presents you with a structure like this and asks you to do an algorithm, you should say exactly this. Say, well, that's an interesting recursive structure that you showed me, and I therefore know that most of the simplest algorithms will be recursive in nature. And now we have to talk about what that actually means. And it just means that the function itself, the recursive function, will call itself. And when you're in a situation like that, you need a terminal case. You need some way to end that recursion so you don't call yourself forever. And we do that here with length. If we have an empty list, we know it's 0 length, and anything else is just 1 plus the length of its tail, right? And this is really, really simple stuff. And then we like to talk about this thing called tail recursive when we're functional programmers. And what this means is it means that not only do we call ourselves, but the last thing we do before we return is we call ourselves. And this is something that is strictly and rigorously defined. And it turns out that if you're in that scenario, then the compiler can do a lot of optimizations to basically eliminate the cost of recursion. So when I look at recursion and I think about, oh, well, if I keep calling this one function over and over and over again, every time I'm stepping through a list, that might get really expensive. And it does. It's more expensive than other ways of iterating through a list. But if you're tail recursive, then it is not more expensive. It's actually the same expensive, and therefore you can have a logical approach to your function design, but you get a performant approach to your execution. And that's like a really desirable thing, to abdicate that responsibility. Let the computer do the work of optimizing it. And they can only do that optimization if you kind of meet the contract. Now, the reason I say this as an aside is because Java does not support tail recursive optimization or other things like that, like tail call elimination and things like that. Java doesn't do any of that. It doesn't do it at the language level. It's something that they are talking about doing, but it's not currently on the roadmap. So this isn't something you can rely on as a Java programmer, but I thought it was important enough to mention so that if you are doing an exploration of functional programming, you understand some of the value of that, and it's something that you can delve into more in another language. So recursion leads us very quickly to a higher order function. And a higher order function is a function that takes another function as an argument or returns a function as its return value. And so this gets into this common concept of functional programming of functions as data or functions as parameters and things like that. And we like this, and we like this a lot in Java in particular, because Java did a lot of effort in Java 8. One of the reasons that Java 8 took so long was because they were introducing lambdas. And lambdas in Java nomenclature is first-class support for higher order functions. So we're back on track now. We're talking about an important functional programming concept that Java has first-class support. I'm sure everyone uses this. Everyone uses this because it's so simple. Like in the past, especially if you were doing things like a callback in a swing application for people that were programming in Java 10 years ago. I just want to give you something that you will call at some point in the future, and I would have to create a class or an interface and then implement that and go to all that work. And it turns out that if you're implementing a higher order function, you still have to do exactly all that work. You have to create an interface, and you have to accept an object of that interface and then invoke the one method. But Java is a programming language. If you've done that work, somebody can pass in a lambda. Someone can pass in an implementation of just that one method, which of course is exactly a function. They can pass that in rather than they personally going through the work of extending that interface and providing the implementation. And we can see here with something called fold left, which is generalized recursion. A common theme in functional programming is we don't like to repeat ourselves. And I just showed you what recursion is, and it's simple, but we don't want people doing that all the time. Just imagine, if you would, that tail recursion became important in the future, and you had handwritten a bunch of recursive code when that was not an optimization, so you didn't care about that. And now you're on Java 17 or something, and that becomes important. You're in a major problem. You have to now reevaluate a lot of code. But if you've abstracted away recursion, where all your recursion is happening in just one point, you could either not have that problem in the first place, or you could fix it in one point and just roll on. And that's part of why generalized recursion is so important, because it is a point of optimization for functional programs. And so we can see here that what the name will be unfamiliar to people that haven't already done functional programming. Just ignore that for now. But this does almost the exact thing that length was doing, except it introduces this combiner and an accumulator. And the accumulator can be anything you want. And the combiner, all it has to do is take one item and add it to the accumulator. And so if we take a look at some examples, well, length, if the accumulator would start with 0, and every element I see as I recurse, I take that and I ignore the element and just add 1 to the accumulator. And that's length. And converting it to a string, every element, I start with an empty string. Every element, I convert it to just called toString in Java, and I append it to my string. And then sum is more complicated. The first two would work on any list regardless of the type, because I wasn't even really looking at the type. In the first case, I was ignoring the object entirely. In the second, I was calling something on Java lang object. But here in sum, it has to be something that's addable, and I've chosen integer. So if I have a list of integers, I can compute the sum by adding them all to the accumulator. Before we get to seeing that in action, it's worth noting fold right, because what fold left does is fold left is recursively iterating over the list from left to right. That's why it's called fold left. And fold right is the reverse. And the difference, if we look at fold left for a second, is fold left is basically combining into the accumulator first and then recursing. And fold right is going to recurse first and then combine into the accumulator. And that's how it implements the difference. And we could prove this, we could walk through it, it's not really important, but these two things exist for a reason, and they exist because of this guy, which is map. We talked about map being this kind of translating operation on a stream, where you can manipulate all the elements of a collection without actually changing the nature of the collection itself. And so I can implement map really easily in fold right by rebuilding a list as I go from right to left. And this has to do with the fact that a list is a head and a tail. And if I were to do this exact same algorithm with fold left, it would reverse the list. And so the order matters. And there's ways that I could work around that. They're really inefficient. So an efficient way to do map on a list is to iterate right to left. And this gets really important from a conceptual standpoint, because you might think, well, what's the difference? Just call one, call the other. How is someone supposed to know? Fold left is tail recursive. And so in a functional programming language, fold left is always faster, except if your accumulator has some advantage to be gained from going right to left instead of left to right, fold right is always faster. And so you have to know some of these things. So there are circumstances where this stuff matters, but not in Java. So you're not folding, you're not doing this stuff in Java, but this is why higher order functions always come out of functional programming languages right away, right out of the gun, because everywhere else, this is where you're doing this like on day 3 of your exploration, or when you're like building your APIs and stuff. It becomes hugely important. So now we're going to get back to those ones we wrote, and again, this is good to walk through in the code example if you're interested. And we can see that we computed length several different ways. We had our recursive, we had a tail recursive, we did it with fold. We get 7 every time. We get the list, 8675309 for people that are old enough to know where that comes from. We can add them up with sum. It's not really important to the song. And then if we look here, this offset list, we basically we map over all those numbers, and we just subtract 1 from every single one, unless it happens to be 0, in which case we leave it alone. So we can see 7564208 was perhaps something else they consider, but much harder to rhyme with, I understand. So this is for people that are interested in this part of the section, get into this source file in the GitHub repository and step through fold in these different scenarios and watch the accumulator build up. It's pretty cool to see in action if it doesn't naturally come to mind for you. So we're going to shift gears. If people remember that map of the implications, now we're back up top where it's something that was implied directly from immutability, which is expressions. Okay? And expressions is basically saying if I write a piece of code, it has to evaluate to something. I'm not going to write a piece of code that does something, that does an action. I'm not going to write a piece of code that does a variable assignment like what we have here. It's not helpful for me to have conditional int and assign conditional int to a value of 17. That's not something that interests me as a functional programmer, because it becomes harder for a lot of the good things to happen. And I've done the best I could with that model. This is legal in Java. I made conditional int final without initializing it. And because I did that, the compiler will now force that all code branches initialize it for exactly one time. And that's a really helpful thing. So if you're even if you're not a functional programmer, if you have a pattern like this, it should always don't do conditional int equals something and then only modify it under certain final uninitialized, and that will force your code to be clearer for what the two conditions are, and the compiler will help you to make sure that it's always set. But we can do better than that, and this goes back to the first version of Java, is we can use the ternary expression of the question mark and the colon, and we can basically get the exact same conditional logic, except we don't have to type conditional int in there. That ternary expression itself evaluates to either 17 or 20 and then can be assigned to a variable. This is better. It doesn't really matter why or how, and it's better in only really minor ways, but in combination with all the other stuff, this is an important concept to have in mind. That we have briefer code here, and we have variables that are unambiguously defined, and we are not copying and pasting tokens around our code. You can imagine if you were doing the above in 3 cases, it would be tempting to copy and paste that. And oh my God, especially if I don't have final, I might have the conditional block for variable 2 actually assigning variable 1, and that would be very hard to detect. But in this case that I have in the after, that's really hard to have that problem. First of all, I'm not copying and pasting, because the thing I was copying and pasting primarily was the token, not the logic. The logic will be different in these cases. There's a whole bunch of problems that are more about how we work than how we code, that expressions improve how we work. So, and there's some exciting things happening in Java in this regard. And now we get into these JEPs. So this is a way for proposing, it's Java enhancement proposal. It's a way for proposing new enhancements to the language. Java 12 and Java 13 have both been released, Java 13 just recently. So the two things we're talking about are available today. I think some of it is still in preview, and what preview means is that you can use it, but you have to set a compiler flag, and it's subject to change, but it's mostly stable. So if you may not want to go to production with some of these things if you're in a regulatory environment, for instance, but they're safe to use, and you should definitely have an eye on these things for when they come out of preview. And if we look at the top, it's similar to what we were talking about before, where we have some switch statement which has a bunch of branches, and ultimately we're just setting one variable. I mean, how many people have written code like this? Probably everyone in the room. And that's not what we want, right? I mean, all these breaks, it's a point of failure. If you miss a break, it's sometimes hard to see depending on how you formatted the code, and then you drop into another case, and it still assigns the variable. The compiler is not going to help you from that. The expression that we see below has many advantages. The first is it doesn't name the variable that it's assigning. The second is an expression by definition, especially in this case, has to be exhaustive. So all paths must return a value, and they must return a value of the same type. So because I've declared expression string below to be a string, every single branch of that switch has to return a string. And even though logically that's what I wanted above, I don't get any enforcement of that. So there's a lot of advantages to having an expression, aside from it being more compact. Now we get to referential transparency, and this is something that we're going to be very brief about because it doesn't apply much in Java, but it leads us to the next bit, which does. So referential transparency basically says that these two examples that I have on the slide are identical. So if I make a variable y and assign it to f of x, and I somehow use y twice, that's the same as me calling f of x twice. Okay? which again, when you look at it on the slide, that is obviously true. But you could imagine that if f of x was doing some computation and emitting a log statement, it would be clear that's not the case. I would be able to tell from the log that it was invoked twice or once from examining the log. Or there could be other circumstances to do that. And we can write code. It's really hard to prove, especially in a single slide. But we could write a program that would take something and tell you if it looks referentially transparent. And I did that. It's in the code samples. And it basically does exactly what you would expect. It invokes it once here on line 6, and then it combines those two results in line 7. And then the second one, it invokes it twice and combines those results. And it just checks to make sure everything looks all right. And we can see that if we had something like a mathematical floor of a floating point number, that looks referentially transparent. And we would expect that. It behaves consistently. And so that means no matter how many times we invoke it, we continue to get the same result, and our program state ends up being the same, whether we invoke it one time or twice or any number of times. And then I wrote another one, and I tried to do this with system current time millis, but it turns out it executed too fast, and it looked referentially transparent. But system nanotime, every time you call that, you get a different number. And so clearly, if I call that once versus calling it twice, I'll get a different result. And so when you run through this, it would say, okay, well, that does not look referentially transparent. We don't really care about that too much, except that it is essential to laziness. Laziness is the concept that the code that you write does not have to execute in the order in which you wrote it. This is like the essence of eager code or imperative code, and it's one of the big differences between what I would consider the top functional programming languages and the non-functional programming languages, because it allows your program to do all kinds of optimizations that you don't really have awareness to. And they would be dangerous if we didn't have everything we just talked about. If we didn't have immutability, we didn't have these properties of functions, we didn't have the ability that things were referentially transparent. It didn't matter not just how many times you invoked it, but where. The order isn't important. Your program doesn't change because as long as the dependencies execute so they're available when they're ready, it doesn't matter if I did steps 1, 2, and 3 in order or in reverse order or something. As long as the answers are available when it comes time to combine them, that's important. And Java's had this from the beginning. And it's had this from the beginning in the context of the class loader. So if I were to put static initializers in all of my Java classes and put print lines in them, then I could run that program and I could see what order they were loading in the class loader. And if I had one I didn't directly reference and I attached that to a button that did a dynamic load of that class, I would see it load when the person first clicked the button. That's what lazy means. That class, it could have been loaded at any point, but we didn't even try until this code behind the button went and said it needed this thing. This is really powerful in terms of letting machines run themselves, and I think a lot of people, especially as we move to a cloud-based environment and we move to a world where developers care a lot more about the operation of their code than they used to, being able to abdicate responsibility in areas like this is really important. Like, we don't want to have that much control over how things execute. We want to focus on that things are doing what they're supposed to be doing. So a more programming example, I typically turn to Project Euler. Is a great website. It's for learning in general, for learning programming in general, and especially for learning functional programming. So for people that are, oh gee, I'm interested in this language, but I don't really know what to code, this is a good place to go to get some different puzzlers. And this is not exactly an Euler puzzler, but it's inspired by one, because they don't like when people publish both their questions and their answers. So if you like this, you should definitely go there for more. So this is talking about the Fibonacci number sequence, where you just take two numbers in the sequence and you keep adding them together to get the next one. So I could start it, for instance, with 0 and 1, and then the third element would be another 1, and the next element would be a 2, because the 1 plus 1 is 2, and then 1 plus 2 is 3, 2 plus 3 is 5, and so on and so forth. It always ends up the same way, whether you start it with 1 and 2, or 0 and 1, or 1 and 1. You got to start it with something early. And it goes on forever, right? And something that goes on forever turns out to be a little bit of a pickle to implement in any programming language. And so laziness is really helpful there, where when I'm defining a Fibonacci sequence in Java, and I'm going to use a Java 8 stream to do it, I implement this supplier, and the supplier is a stateful object that in this case knows the last two numbers. So as long as I can prime the pump, and I do this when I create it just in the constructor, I say, okay, we're going to start with 0 and 1. So the first time you call get on this thing, it's going to produce the number 1. And then the second time you call get, it's going to produce the number 2, and so on and so forth. And I can tie this supplier to a stream, And now, if I were to call get on that stream forever, what would happen in this case? Let me just check the type. So we would basically keep going until I overflowed along, and either the program crashed or it started repeating itself in a weird way, or who knows. But it would be undesirable if I got to that point. And I could solve that with a big decimal or something that can grow infinitely, and then it would go until I ran out of time or stack, or it thrashed the heap to the point where the operating system ceased. And that makes it hard to write a program that terminates or does what you want. And so we can see here, so the problem we had was the first 17 odd Fibonacci numbers. We can do that very quickly. We do a filter to get just the odd ones. We talked about filter a little bit before. And then we add this thing limit. And limit says, hey, well, just get 17 of these things. It matches up very well with the contrived question. And so that makes it no longer an infinite stream, but rather a stream that is at most 17 elements. Limit will still work even if it's fewer, I think. And then reduce will compact them all by applying the sum to a zero initialized accumulator. It does exactly what we said. We say, I want to add the first 17 odd Fibonacci numbers. When I read this, I can tell you this number is adding the first 17 Fibonacci numbers, odd Fibonacci numbers. That's exactly what that program says. And this is one of the things that leads to clarity. Now that's very helpful when you're solving, it's no surprise that functional programming inspired by mathematics is very effective at solving mathematical problems. So I know that's not always the case for people, but it is the case in a lot of cases. If you're doing data analytics or something, you should already be doing these things. You can check my math, but I'm pretty sure that's correct. So we're going to take a little shifting gears here. I just want to point out that all the themes we've been talking about, every category here, what we're focused on rigor instead of policy. Especially when we were looking at some of the expressions, the conditional versus the ternary operator, or the two switch statements, the switch statement versus the switch expression. They were functionally the same, except in one case it was our mind that was enforcing what we wanted, and in the second case it was the compiler. There's rigor there, and that frees our mind to focus on more important things. We're always focused on limiting the possibilities, like being able to say something like, hey, you don't have a side effect, you don't do anything, you don't touch anything that isn't one of your inputs. That's limiting, right? But limiting can sometimes be favorable. We've all seen what happens when you let software engineers run hog wild without any limits or constraints, right? They do terrible things. I've been one of them, right? So we want limits. Like, limits actually makes our job easier. We just have to be selective in choosing the right ones that allow us to continue to be effective. And then we want to prevent the unexpected. And this brings us to another category. So when we talk about functional programming, we don't typically talk about type systems. In the beginning. It ends up not being important. Like, all those concepts, if you think about it, there were types in the examples because it was Java code, but I never really talked about the data type. And everything I talked about, the data type didn't really matter. Like, when we set a list, the details of the list, but it could collect any type of object in the list. Like, sometimes we saw a string, sometimes we saw an integer. We never really care. Like, we can do recursion and higher order functions and laziness and expressions. We can do all that stuff no matter what we're talking about. But Java's a type language, and Java has some features, some JEPs that are on the roadmap that are coming soon that are very type specific. And so there are definitely mathematical influences of type systems, and there are functional programming languages that have a lot of rigorous type systems that do that. And so it's not relevant, but it's not typically what I would start with. But we are going to look at, in particular, algebraic data types and pattern matching, because that's an area where Java has functionality that's coming very quickly. So algebraic data type, we're going to skip that one also. An algebraic data type is a data type that is rigorously defined as either the sum or the product of individual data fields, or both. So something that is the product would be like a structure, like this employee. The employee is a bad example. Some structure that has 3 fields, that is a product type. And the reason they say that is because the domain for that structure is the Cartesian product of the domains of the individual fields. And then we have a sum type, which is additive, which is an either or. So if it takes something like a Boolean, could be true or false, we can convince ourselves that that's actually an algebraic data type. It's not a useful one, but it only has these 2 known states, and they actually don't store any data. It's the nature of the side. So that's where the name comes from. It doesn't. I found that to be completely unhelpful in understanding these and what they are for. So we're going to look at an employee here. He has a name, a start date, and an end date. And we have this Boolean flag for whether or not the employee is a current employee. And I think that, especially if we can go back as far as, we'll say, the late 90s and early 2000s, a lot of people had structures exactly like this and may still, and there's a lot of database tables that are exactly like this. And you can get rid of the Boolean, and we could say, oh, well, end date is nullable and the start date should always be there and stuff like that. You can see where I'm going with the rigor of the type systems. Like, these are all awful answers. But we can make it work, and we can write a get milliseconds of service, which I wrote because I don't want to do date logic. And so if you're a current employee, your milliseconds of service is now minus when you started. And if you are a terminated employee, it's just your, when you were terminated minus when you were started. Simple logic. An algebraic data type in this case would make it so that the end date doesn't exist. It's not even part of the data structure unless the employee's been terminated. So there is no condition there. It's this data structure is a combination of intent and data values. And so you avoid these, ignore this column and this condition, ignore this data field in this condition, don't use it as part of your computation. Imagine the scenario, of course, where someone gets terminated and then rehired. And now, am I certain that the end date was properly cleared when they were rehired? Am I certain the logic of my program is going to compute their milliseconds of service correctly? It's a pain in the butt to figure out. Like, it's just logical contortions you have to go through to convince yourself you've done it correctly. But if end date is only available for current employees, for terminated employees, you're not going to have that problem. When you make them active again, the data field is gone. It's not nulled out, it's not zeroed, it's not deleted, it's no longer part of the data model. So there's a huge amount of value in this, in the theme of functional programming, of making sure that you can never be in this circumstance, which is logically incomprehensible. And so we could implement an interface for employment dates, and then we have this intent. So in the case where employment dates for a current employee, it's just the one thing. And employment dates for a terminated employee is both things, right? And this is the essence of an algebraic data type right here. And then when we get these other JEPs, and for people that have the slides, these are all clickable. You can go straight to the documents. You can see like how they talk about this future functionality. We'll be able to use new keywords. Okay, so what sealed means everything that implements employment dates is in the same source file. It's more complicated than that, but that's like 90% of it. Super helpful, and that's helpful for two things. The first is it prevents mistakes, like someone else supplying a new employment dates. But when we talked before, I said like expressions are exhaustive. If I have a switch expression off one of these things, I no longer need a default. If I handle both cases, that's really powerful, because if I have a default and add a third one, that default's going to hide a programming error. If I explicitly say the two cases with no default and then I add a third one, that switch expression will break. My compiler will do the work for me. I no longer have to think about it. I don't have to audit my code and figure this stuff out. Really valuable, from not in the code we write, but in the way we write code. Now record is basically saying this is a simple class, and I'm willing to trade a compressed syntax for certain limitations. So by default, a record will make every declared field public and final, just like my first example, right? We're heading towards immutability as a native function of a native feature of the Java programming language, right? This is the direction Java is headed, as well as a lot of other people. It also, no longer do I have to generate my getters and setters in IDEA and then wonder if I need to regenerate them 8 years later when I'm looking at my code base and wondering how many different versions of IDEA generated equals in hash code. Like, are they all consistently generated? Who knows, right? Once you get past like 18 months, you have no idea. But in this case, the Java compiler will generate equals and hash codes for these things. And we looked at that example of the person in the set. That was an abuse of the contract of equals and hash code. Like, that's exactly what I was showing there. They're very hard to get right for mutable objects, and I think most people that have spent a lot of time with Java would say something like, you should never include a mutable field in either equals or hash code. Definitely not hash code. It's a hazard, right? These things say, oh, look, we're just not changing anything. Everything's public, everything's final. We can generate getters if we need them. The compiler will do that. We're not going to maintain that at the source level. So our source is simpler. We know exactly what we're getting. And then when you get to things like serialization frameworks can get much more aggressive in how they deal with these things. Because for instance, that like the bytecode version of a serialized record doesn't matter. Like, who's running into that problem in Java, right? Where it's like, I have some class, I got to make sure that when it loads, when it deserializes, the method implementation is the same as when it was saved. Like, there's no such problems here. You can extend these things in different ways, and you can do stuff to curtail yourself, but you are limited. And my recommendation is to keep them as just dumb data objects and externalize the code that operates on them, and the word for such externalized code that operates on data objects are functions. So we're all headed in the same direction with that stuff. And now we get to pattern matching. When I'm obviously a big fan of Scala, and when Java 8 came out with streams and lambdas, which were both, really, they were big selling points of Scala over Java. A lot of people said, oh, well, they're not going to use Scala anymore now that Java is just as good. And I'm like, pump the brakes on that. Scala doesn't have destructuring pattern matching. And everyone's like, what's this guy talking about? This has always been my favorite language feature of Scala in particular. And Java will be getting it soon. This is on the roadmap. It hasn't been allocated towards a specific JDK version. Records is essential before you even get all the way here, and records is either 14 or 15. So we're headed in that direction, but no one knows exactly when these things will be available. If I wanted to extract data from that algebraic data type I just wrote in Java today, I would have to write the visitor pattern. And this is great. All of my code examples fit on one slide, except for the visitor patterns on two. And anyone that's used it knows that this is actually an instructive part of the example, because the visitor pattern sucks. And you're going to write a ton of code to do something that is very simple. But what we want is we want to be able to perform an operation on the different branches of the algebraic data type in a consistent way. And we want compiler enforcement that all the right things are happening. And that absolutely happens the same way that if something was sealed. Like, this visitor implies there's exactly 2 implementations of employment dates. And if you added a third, it wouldn't be accessible. So the visitor pattern's already confining people in a way that's really attractive from a functional programming standpoint. We'll be able to do that in better ways in later versions of Java. So this would let us, so we have like the current employee is one implementation, and when it visits the visitor, it passes its own this pointer. So if I'm on the outside, I only know that this is an employment dates object, but it knows its own type. And so the visitor is basically, without anyone knowing the exact types, I can circle through the object and the visitor and come out the other side, and it will execute a specific piece of code on exactly the right type. So it decomposes that without external analysis, which is really useful. So if you can invoke someone else's visitor, that's awesome. If you have to write the visitor yourself, I'd like to say it's a bad day, but it's usually more than a day. So now we have a way of doing that millisecond office visitor, and so we can push all this stuff through. And this is the same logic that we saw before, but it's in the visitor pattern. And then now our algebraic data type is, instead of it doing that logic of figuring out the case, it can just basically decompose based on the types and get the right answer. And we basically did the same thing. And look, I'm not even going to try to argue that it's better. We're trying to do the same thing we did before in a more rigorous functional way, and it took us like 30 times as much code. I mean, it's just awful. And this is why people don't do functional programming in Java very often. This is why the visitor pattern is only used when it's like you have a tough problem to solve, and it's like all the other solutions are worse. In this naive example, this solution is worse. But when you have these enhanced switch expressions, then the functional answer is much better. And so in this case, we can switch on the type itself. So we have this employment dates object. We can switch on that. And if it's a current employee, we can extract that one data value from the structure. And then we can write code that only has access to the one value that's in scope. So if you are a current employee, your computation can only take into account start date. This is hugely valuable, even if it's functionally identical to the code we wrote before. And then, of course, with a terminated employee, we have access to both. And now we're going to ignore, as functional programmers, that this is accessing something out of scope, and it's a major violation to be having a system clock. We're not worried about purity in that sense there, but we are worried about limiting our scope, and so we're able to achieve that there. And the other really nice thing about it is, in the first case, I was forced to encapsulate. I had to tighten all that stuff up myself because I was worried if someone else was going to access those fields, they might not do it properly. They might not call the Boolean. They might do a null check I wasn't expecting or something. I had to own that. But here, I could make this data value public, and I could let other people do this destructuring operation because there's really only one way to do it. and they're not going to be able to screw it up because the confines are too tight. And so I can have a more expressive API that gives greater access to my callers with built-in defense mechanisms, and I get that just by virtue of my programming paradigm. So that's why we're even talking about type systems today, is sealed and record, really exciting features on the Java roadmap in terms of compressing code and being more clear about where your data objects are versus your more function-rich objects. And then the destructuring is, I think, a really big part of, it's going to be an interesting time for language selection because the destructuring pattern match is going to lead to a lot of even more expressive, tight Java code. And it's going to, I think, take away some of the advantages of especially the JVM-based functional programming languages. So that's going to be a really good thing to look forward to. Most people, when they talk about functional programming, especially in Java, they start with optional. So I've saved optional for the last. Let the record reflect that we're 45 and an hour into the talk. It's the first time I've used the word, and now it showed up in a couple of the examples implicitly, but we didn't draw it out. Now, optional is an algebraic data type. It's an algebraic data type that either has no value whatsoever or has some value of a data type. But it turns out it's not implemented that way in Java. So when you get switch expressions and when you get destructuring pattern matching in Java, you won't be able to use them on optional. And you see them a lot in other languages as like a way. So it's kind of an interesting, they could have made it an ADT when they first implemented it in Java 8. But then it would have been really cumbersome to interact with because of the visitor pattern. So they made it optimal for that environment, and as a result, they won't be able to ever change it. Now, it's not really that big a deal, but it is worth noting that this is exactly the one of the issues with Java and other languages is that an optional structure lets you avoid things that are bad, right? And the three things that are bad, we have sentinel values are bad. So if I call, get active user ID, and that returns -1 to represent no user, and it returns some positive integer for a user. That's a sentinel value, a special value that's buried within the type signature, and you have to decompose it through policy. Optional lets you represent that through rigor. I could return no, there is no such user, versus some user ID. So that's good. Unnecessary exceptions. Like again, I could have implemented get user ID, get active user ID with an exception. Throw an exception, no such user. But this doesn't seem that's that exceptional. It's kind of an expected case, although not a desirable one. Option would let us get rid of that. So none implements that. None implies that what you wanted isn't going to happen. You need to find another way or enter a different control flow. And then null, of course, is designed to get rid of null. And if you think about it, null is a sentinel value. Null is a special value that fits within the type signature of something and lets you indicate something other than an actual value. So it's really just a special case of sentinel values, and optional lets you get out of it. And what it does in all of these cases is it basically presents any exceptional case to the type system. And that lets the compiler make sure that you're doing things correctly. So that's it is a valuable thing. It's not particularly useful to say something like, well, optional lets you get rid of all your nulls, and then people are calling .get all the time, and they're getting no such value exceptions instead of null pointer exceptions. That's not an improvement. So that's not what people were talking about. We're going to take a quick look at some of those things. So if I had like a divide function that took a numerator and a denominator, I could implement this a lot of different ways. I could let the compiler do what it's going to do and just throw the operation into Java. And I think it throws a divide by zero exception. I didn't actually try it. I can't remember. Or since I'm returning a double has a nan value, not a number. I could return not a number for division by zero, right? And just rely on people to figure that out for themselves. I mean, some people, especially junior programmers, may not even know there is such a thing. They probably also don't know there's a positive and negative zero in a double, and so have fun with that one when you figure that out the first time. Or in this case, I'm going to just make it return an optional. So I'm just saying, look, my range is everything but zero. As long as you don't pass in zero for the denominator, I'm going to give you the actual answer for this division problem as best I can. And if you do pass in zero, I'm just going to return none to indicate that I didn't do anything, right? And so that's better. It's better in a minor incremental way. There's nothing. I'm not going to get too excited about it, but it's a clear demonstration of a case where you would produce an optional out of what you're doing. It's not as useful if I'm like reading a value from a database and like none is really really bad, and there should be something there, you should probably throw an exception. Like, you don't want anyone to continue. So you have to be selective in how you represent things. Now, consuming optionals, I have three examples here. If I'm getting a value from an optional, a lot of people, especially if you're not functional programmers, you'd be tempted to write the top code. I check to see if it's present. If it's present, I call get. If not, I'll return some other value. Really common pattern. Or I might just call .get without doing any of this, and just let the exception throw, which again, I already said is a terrible idea. So I can replace that with my optional dot or else with the default value. This will always return a value of type T. It will either return the value contained in the optional, or it will return this default value I provided, which has to be the same type. And it's much more expressive. It's one line instead of 8. It's better in every way. And you talk about, like, even writing that first function. Like, it feels unclean to have to write a utility function like that. And think of all of, like, an area where languages are stronger than Java is like the richness of the string API. Who here has a string utils class, and how many functions does that have? And how many do you wish were either one-liners one way or another, being able to, like, filter a string or apply some transformation to a string, or they should just be part of the API. So it's better to not have to go into your own function context to do something like this. Here's like a safe toString where I have an optional and I want to convert it to a string, right? And I'd like to, if it's none, that's okay. I'll just keep it as a none. But if there's something in there, I got to transform it. Same thing here, where so if it's present, then I'll just make a new optional and I'll convert, do .get toString. Like, it's a lot of work. It's not what you want. That's exactly what map is for. Map's a transforming operation, and it appears on optional. I said one of the first things. If you see a map and a flat map, you're probably in the right area. Call them. Transforming a single value in the context of an optional is the same as calling map on a stream. When there is a value available, transform it. If there isn't, you don't have to do anything. It will conditionally apply for you. And then flat map is available on optionals as well. And I'm using part of why I wrote divide in the first place. So if I might have some double, I can flat map that with divide. And so if there was nothing in the first case, it stays nothing. If there was a double, it will do the division, and it'll be a sum of the result. And if there was a double that I end up trying to divide by 0, it will change that sum of a value into a none. So there's a manipulative value of flat map. So map only works on interior values, and flat map lets you stretch out a little bit and influence the structure that you're within. And that's like the easiest way to think about it as you're entering the world of functional programming. So I've shared a lot of my opinions, as well as a lot of facts and detail on a lot of the facilities within Java. I just like to share a couple other I thought pretty valuable opinions from random people I found on Twitter. So this first one from Mateus, he's talking about not talking about OOP versus functional programming, but talking about the individual concepts and how those are applied in your programs. Focus less about what is called and more about what you're achieving. And you'll see that the first half of stuff, these are all things that I think I explained pretty thoroughly at an introductory level in this talk. And then this Alex here is talking about Scala in particular, but you can see that he's talking about like what's hard for people entering Scala and how it's not, like the programming language itself isn't what trips people up. It's a mindset change as you go, and you'll see a lot of the very similar things that I was just talking about. And I tried very hard to not use the word monad. It slipped into this tweet, so I apologize for that. But we'll pretend we didn't do that. So this is a functional programming talk without monads. And then a lot of the reasons I'm aware of this, and a lot of the reasons why I'm talking about it, is because of the work of Brian Getz. His name is all over the enhancement proposals for all this stuff. He gave a talk last year in Philadelphia and at other locations about some of the roadmap features, especially the functional programming inspired ones. The video is here on the slide for people that want to pull the slides and watch it later. He's a guy to watch and follow and read the stuff he's writing if you're interested in this topic, especially functional programming in the context of Java. And he's a really friendly guy and willing to talk with people of all skill levels about these topics. So for alternative opinions, I'm happy to talk to people as well. But those are three people you can engage with if you want other opinions about some of this material. So that's the end of the material I was providing. I have some recommendations for people, and this is, again, this is more if you're a Java programmer and you're trying to get more into this stuff. So just use Final more, drop it everywhere. More constraints are better. If you put Final too far and people come to you and complain, oh well, this code I wrote that depends on yours doesn't compile anymore, you can always throttle it back, but at least you'll know. Oh, I didn't realize people were changing that thing, right? But now you know. So more constraints are better. Try to write raw data objects that are immutable, and that will give you a step in the right direction. And then when record is available, you'll just make it a record, and you'll drop a bunch of code, and you'll already be set up for that. So like final leads to a lot of good programming patterns. Any constraints at all, I think, do, but final in particular. If you get the chance to use Java immutable collections, you might as well. At this point, I wouldn't go out and get another library. I wouldn't use persistent data structures because of the lack of recursive optimization. I think they're not going to perform to your liking. It's not going to be a great situation. They're great to experiment with, but it's not where I would go for production in Java. But you should take advantage of the facilities that are available to you. Try to get rid of all the Sentinel values in your code and have that attitude. Like, be able to read code and say, this right there, that's a Sentinel value, that's bad, we're getting rid of that. One way or another, I don't care how. It could be an exception. It could be not allowing that case. It could be confining your inputs such that that branch is no longer available. It could be using optional. It doesn't really make a difference whether you do that with FP or any of the other available techniques, but you should be getting rid of Sentinel values. Here in 2019, that should no longer be a part of people's programming vocabulary. Don't get into ADTs yet. Algebraic data types are not for this version of Java. Just don't. Just wait until you have destructuring pattern matching in Java, whatever. I don't know when that's going to be coming, but that's going to really unlock the door to that element. So in terms of this talk, focus less on what I was saying about the type system and that final category, and focus more on the concepts from the first part. I have some recommendations for people that are more on the intermediate side. The advanced people probably are not interested in anything I said today. But if you have an optional, don't be in a hurry to call get. Don't be in a hurry to get rid of the optional. A lot of times what you want to do is you just want to pass it forward. If I'm in a situation where I could have gotten an optional and I need to act on it, I'm going to map and then I'm going to feed the optional back out the other side, because the thing I call might produce nothing. Therefore, I might also create. And this is secret stuff. This is going to lead you in the best possible direction for functional programming, especially if you do the next one, which is to create more containers like optional, more things that contain data and encode behaviors in that container, and you leave things in the container as long as possible. So I'll spot you an easy one. It's called either. So optional is either nothing or something. Either is either one thing or the other, and the one thing might be an error condition. So rather than just say, oh, I couldn't divide by 0, you get nothing, it would say, oh, you get this side of the either, and it's a divide by 0 error. Versus if you get this other thing, it's the actual right answer. So writing that is a valuable exercise. You'll learn a lot, and then if you introduce it in your code, which you should not do in production code for Java at this point, but as an instructive exercise, if you go and do that, and create containers like that, and then write code that tries to keep it in the container as long as possible, that will lead you in the right direction. This is leading you in a direction for a word that I mentioned once and promised not to. If you want to learn functional programming, Project Euler is a great context to do it. If you don't have a better way to do it, you should start there. Lots of, especially early on, really fun little math problems. You can solve them any number of ways in any number of languages. Pick a functional language, solve them in that language, keep going. If you can make it to problem 20 out of like 800 or something, if you get to 20, you're doing really well. Some of them get really hard really fast. But if you're not enjoying it, just stop. But you should be able to do at least, I'd say 5 to 10 of the first 20, if you're going to be a successful functional programmer without trying too hard. Java is not a great language for learning functional programming. It's becoming a better and better language for applying functional programming. If you want to learn functional programming, I recommend you switch to another language for the context of learning. I like Elm, I like Scala. Elm is first. Elm is first because there's very few choices in Elm. They do a really good job of having a rigorous mental model, and you follow that and you learn. Scala is the Wild West. It's like the C++ of functional programming languages. There's so many choices, so many opinions, so many people pulling in different directions. It can be tough to navigate when you're learning. It can be very effective when you're at like an intermediate or an advanced level, but you have to be qualified to make those choices, and a beginner just isn't, and it could potentially be a disaster. Now, I learned functional programming in college, but more recently I spent most of the time learning in Scala, and I have some scars from that experience. I don't have a book recommendation, but really it is a case where it's a good exercise to get a book on functional programming for a language that you like or favor. And do the exercises. Like the exercises like, hey, handwrite fold and now implement map in fold. Like that's a really good exercise, and it's not easy. Like it's on the slides there, it's in the code deck, but handwriting that, you know, not just from memory, but handwriting it intuitively as this makes sense to me, that's a really, really strong position to get to as a functional programmer. And there's tons of other exercises as well, so I advocate for that. So here's links to the slides and the GitHub repository, and with that I have time for questions.
So is the point of functional programming